Okay, hi everyone. Thanks for coming to the Graphs and Matroids seminar. Today we have Archontia Giannopoulou, who's at the University of Athens, who's going to be talking about a matching theoretic flat wall theorem. Go ahead.
Hi everybody. Thank you very much for inviting me to give this talk. I'm very happy to be with you even from a distance. So I'm going to talk about flat wall theorem in terms of matchings. Graphs with perfect matchings. The results I'm going to mention are joint work with Sebastian Bitterecht, and also the idea behind many of these slides is his. I would like to apologize in advance. Some slides are well written, some are handwritten, and it might be impossible to read my letters. I will take the excuse of the power outage. I have no battery, so I couldn't finish all of them nicely on time. Okay, so first I will discuss a bit about the structure of the talk. I'll have to introduce some basic notions of matching theory, actually maybe a bit more than a few, discuss the motivation, and then finally conclude with the flat wall theorem and the matching setting. So the story as we know it is that we are all very well aware of the graph minor theory, of structural graph theory. And we also know that there are results on digraphs trying to raise the results from graph minors to the digraph setting. And in this talk, we're going to discuss about the structural bipartite matching theory. So we're discussing about graphs that are bipartite and all have a perfect matching. And actually, while I've written this whole picture like that, like we have graph theory, digraph theory, and then matching theory, actually we could say that in a sense, matching theory is between those two. I will try to explain why during this talk. First of all, one of the reasons is that graphs with perfect matchings are actually not directed graphs, they are simple graphs with some specific structure, but also can be seen as digraphs under some specific transformations. So to make clear, we all know a matching in a graph is a set of edges that do not have any common vertices, and it is matching if every vertex of the graph is covered by some edge that belongs to a matching. Okay, so this is our set. Graphs that have perfect matchings and are bipartite. And the objective, or one of the objectives in structural graph theory, or any theory, is to describe the structure of graphs that either do not contain some fixed graph as a substructure, whatever this is, it might be a minor, it might be a subgraph, an induced subgraph, etc. And either we want to find some minimal graphs that are forbidden and describe this graph class, or we want to find the detailed structure of the graphs that forbid some specific substructure. One of the best well-known celebrated theorems is Kuratowski's theorem. We all know that planar graphs are characterized by excluding the clique on 5 vertices and K33, the complete bipartite graph on 3 and 3 vertices. Right. Of course, Wagner's theorem, which characterizes K5 minor free graphs. These are built, we all know, by planar graphs, and Wagner's graph, which is this graph here, and more generally, the Robertson-Seymour theorem, which characterizes the structure of all graphs that forbid some edge as a minor. So this is the scope of structural bipartite matching theory that we're discussing today. We want to describe the structure of some graphs that forbid some structure, some graph with the perfect matching as a subgraph. So let's discuss a bit about matchings and about directed graphs. So even from 1987, there was some characterization of digraphs, of even digraphs. I don't want to discuss what this is about. This is kind of out of scope. We will see some equivalent definition. And we got there the notion of butterfly minors, which is an appropriate notion of minors in directed graphs. And we actually can see that these graphs are characterized by excluding an infinite antichain of directed graphs. Then came the notion of direct attribute, and with it came the conjecture that large direct attribute implies a directed grid. Of course, then came the result, and then the directed flat-hole theorem. And the reason I mentioned the directed flat-hole theorem and the directed grid theorem is that we kind of need them, or not necessarily need them, but use them in order to obtain the flat wall on bipartite graphs with perfect matches. Now, at the same time, or actually even earlier, there came a characterization of graphs. Pfaffian bipartite, I'm not going to say yet what Pfaffian means, but the case is that they became we got a characterization of bipartite graphs in a sense of an excluded minor, whatever minor means in our matching set. And eventually, actually, it can be seen that these two results essentially say the same thing. They kind of merge digraphs to bipartite graphs. They connect those tools together. Okay, the tight cut decomposition, which I'm gonna need to mention later in order to set the frame of what we're talking about, and also the structure of Pfaffian bipartite graphs, which also gave an algorithm for identifying whether we have a matching minor in the graph. So I'm not going to introduce the basic notions on matching theory, which we're going to use to state our results and see the connection with diagrams. So here come the handwritten slides. We're going to say that the graph is matching covered when every edge of the graph belongs to some perfect matching. This is not matching covered because this edge here will never be in a perfect matching of the graph. If this edge is in a perfect matching or this edge in a perfect matching, then this vertex here will not be matched. However, this graph is matching covered. Matching covered means that the graph is connected, and also every edge of the graph belongs to a perfect matching of the graph. So we can actually see now that whichever edge we want, actually we will, because of the fact that the graph is symmetric, we can actually see that whichever edge we want, we can put it in a perfect matching, whether it is one of those, etc. Now, a tight cut, which I mentioned earlier, is a specific cut in the graph where for every matching, if we look at the edges of the cut, whenever you give me any perfect matching of the graph, only one of these edges will belong to it. Like for every matching, exactly one of the edges belongs to it. And we can use tight cuts in order to decompose the graph into smaller parts. Actually, it's like we cut along the edges, and each of the other parts becomes a single vertex. So actually, in order to show it and give a better idea, here on the left, we cut, then we identify all this part in one vertex. We've got the smaller graph, and same for this side. And actually, this graph is matching covered. It has no non-trivial tight cut. What does it mean that it's non-trivial? It means that when we have a cut, both of its sides, its source, as they're called in matching theory, have more than two vertices. And we can keep cutting and cutting and cutting until we reach graphs that are matching covered and they have no non-trivial tight cuts. So tight cuts are trivial. And what was shown by Lovas is that the list of graphs for which we will end is unique, no matter how we cut, how we choose the tight cuts, in which order we choose them. In the end, the list of graphs we will have will be the same. The building blocks will be the same regardless of how we cut. And these are called braces whenever we're discussing about bipartite graphs, and bricks when the graph that has no trivial, that only has trivial tight cuts is not bipartite. So of course we will only consider braces because we're only considering bipartite graphs. I'm actually gonna need all those definitions when I'm discussing the statement of the flat wall, and in particular when I'm discussing the flatness. So another definition I'm gonna need is that of matching minors. And for that I'm gonna need, unfortunately, some more definitions, which is that of a conformal subgraph. We say that a subgraph of a graph, okay, I'm not going to repeat it, we're always considering perfect matchings and bipartite graphs. Let's say just perfect matching whenever we're given a subgraph, and whenever, after removing the vertices of the subgraph, the graph that remains has a perfect matching, this is conformal. We will call it conformal. So in this case, this is a conformal subgraph, and vice versa. If the matching is fixed, if we know the matching for which the remaining graph is conformal, then we can call it M-conformal, in the sense of the name of the matching. And finally, we define bicontractions in such a way that whenever we have a vertex of degree 2, we contract both of the edges that are touching the vertex, that are incident to the vertex. So if we think of minors, we know that a graph is a minor of another graph. It can be obtained after contracting edges in a subgraph of the graph. So similarly, now, a graph is a matching minor of a graph if it can be obtained from a conformal subgraph via bicontractions. And the reason we need those definitions is that essentially whenever we are applying any sort of transformation on the graph, we actually want this transformation to preserve the fact that the graph contains a perfect matching. So we will always, of course, consider that no matter what we do, we remove multiple edges, we remove loops, and every edge that is contained now in the graph belongs to some perfect matching. If it does not, then we don't have to bother ourselves with these edges, we can just forget about them. Okay, and finally, one more definition, and this is the definition of M directions. Basically, what I said before, and maybe please forget half of the screen. Let's look at the picture. Whenever we have a bipartite graph with a perfect matching, by fixing a specific matching, we can actually go to a specific directed graph. So what we do is that we have that, let's say the white vertex is in one of the classes of the bipartite graph. The black vertices are in the other class. What we do is we contract the edges that belong to the perfect matching. We preserve all other edges, and we give to them a direction. We give them an orientation. And this orientation, we can fix it. In this case, we just decide that we give a direction from white to black vertices, from one corner class to the other. Right, so from every graph with a perfect matching and every perfect matching, we can obtain a directed graph. Now we can also go back from any directed graph, we can obtain a graph with a perfect matching. And the way to do this is that whenever we have a vertex of the graph, we replace it by an edge. We split it in two. We get one of the vertices in a color class, the other vertex in the other color class, and we connect the outgoing vertices in one color class and the incoming in the other. We just choose whichever one we want. So actually, in a sense, whenever we have a graph with a perfect matching, from this graph, we can go to many different directed graphs, depending on the perfect matching that we choose. So graphs with perfect matchings are not exactly the same as digraphs. This is what I'm trying to say, because a single graph can go to many different directed graphs. And of course, a directed graph can turn to one graph with a perfect matching. But what happens is that directed paths and cycles on directed graphs, when we go back, actually whenever we go back and forth, these correspond to paths and cycles and matchings. And of course, because we were discussing about matchings, the path that we're considering are alternating paths. It means that they might start from an edge that does not belong to the matching, they will follow an edge that belongs to the matching, non-edge, edge, non-edge, edge, non-edge, etc. So alternating cycles go to directed cycles. Alternating paths go to directed paths, and vice versa. And an order one separation, a separation that after we remove it, we have edges only towards from one side of the graph to the other, corresponds actually to a tight cut. So this vertex here, which is actually a cut vertex of the strong connected component, corresponds to this tight cut over here. And in a sense, butterfly minors correspond to matching minors. I will again not go into many details because I will need to define more and more things. So now that we have the basic and more important definitions, let's start discussing structure theorems on graphs with perfect matches. Again, I have not yet defined what Pfaffian means, and I will do it later, but let's say that a graph, a bipartite graph, has some very specific properties, if and only if it excludes K33 as a matching minor. And K33 will be important for us in the future as well. And a brace, which is actually a bipartite graph without a tight cut, does not contain K33 if and only if it can be built from some specific building blocks, which are the Higgwood graph and planar braces. So basically, similarly to Wagner's theorem, where we have that all graphs excluding K5 can be built from Wagner's graph and planar graphs, we have that now braces that do not contain K33 can be built from the Higgwood graph and planar braces by some specific by C4 sums, which are similar to clique sums in a sense. Basically, if we have a graph G1 and this graph has a 4 cycle, and we have another graph G2, and this graph has another 4 cycle, what we do is that we can identify these 4 cycles and maybe remove some edges of the cycles, whichever ones we want to remove. But what is all this? What is the motivation about going into graphs with perfect matchings? And why think about the theory? Why do think about the structure of graphs with? I'm sorry, my phone was ringing and hijacked my headphones. So, what is the motivation? Of course, matching theory has been studied by Lovaas and Plummer already in not a completely different sense, but in a different sense. And actually, even for bipartite graphs, we have notions of connectivity as well, which I didn't mention. So what's the motivation? Well, let's start by a very old problem. It was a problem in statistical mechanics regarding crystal lattices, and the question was, if we're given a grid and we're given dimers, which are basically polymers of two elements, how many ways can we place these dimers in the lattice? So of course, this is the same as asking how many ways can we create a perfect matching? And so now the problem, of course, it's more general for us. If we don't have a lattice, we have any graph. How can we count the number of perfect matchings in a graph? We know that finding a perfect matching is actually, or deciding if a graph has a perfect matching is polynomial, it's easy. However, in order to count the number of perfect matchings, we're actually in the class sharp-p complete, which is a counting class. It basically means, I've got a definition in some slides later, it means that we count the number of accepting computations of a non-deterministic Turing machine, a polynomial non-deterministic Turing machine. And in 1967, Kostelin, I'm not sure if I'm pronouncing the name correctly, I'm sorry if I'm not, defined Pfaffian orientations in order to solve this problem on planar graphs. So what's a Pfaffian orientation? It's an orientation, we orient the edges of the graph in such a way that every M alternating cycle, so actually a cycle that goes between edges and non-edges alternating, has an odd number of edges in its direction. So for example, in this case, if we see this graph, it has a perfect matching. If we look at this cycle, we have 3 edges going along one direction and 1 edge going the other, so odd. Same for this, etc. So a graph is Pfaffian if it admits such an orientation. And this reduced the problem to the computation to that of the determinant of the matrix. So instead of counting the number of the matrices, we can compute the determinant of a matrix instead. And some other equivalent problems. So I'm not going to discuss about Pauli's permanent problem as well. But what happened is, like, actually with those 2 papers that I showed before, that equivalent that somehow merged directed graphs with perfect matchings, is that a bipartite graph G is Pfaffian if a domain does not have K through 3 as a matching minor, and which means that actually the direction, the directed graph that we obtain from G with M, which is a matching of G, does not contain any odd bicycles as butterfly minors. And what are odd bicycles is essentially like cycles of odd length which have both edges. So this would be 3, 5, 7, etc. So actually what happens is that we're given a graph for which, in order to be Pfaffian, the directed graph has to actually exclude an infinite antichain in terms of directed graphs. In terms of matchings, we only have to exclude 1 graph as a matching minor. As an example, this graph here, which is called the Möbius ladder, actually has a K through 3 matching minor and then M direction.
I'm not seeing a graph. Oh, there we
I'm
go.
sorry?
Okay, sorry, I was gonna say something too. I think it just, the slide was lagging behind for a second, so we couldn't see the slide that you were on, but I think it's okay now, so.
Okay, I'm sorry.
It should be fine.
So
Sorry about that.
You can see it now. It's okay.
Yes.
So this is the graph. It contains a K through 3 matching minor. We can find pretty much the cycle of the matching minor and the edges that are connected, basically because of this here, and we can find the odd bicycle. So now that we've discussed, I'd say, quite a bit about matching theory, let's just start discussing flat walls. What are, of course, the tools that, is it working? Okay, because I'm seeing Zoom telling me that my internet connection is unstable. So anyway,
Okay,
so what are the
it's a
tools of
little
graph
bit,
minor theory? Well, yeah,
sorry, it's a little
I'm
bit
sorry.
laggy, but we'll try to push through.
Okay, thank you very much. Thank you for staying with me. So what are the tools of graph minor theory that we use for the flat wall theorem? Actually, that led to the flat wall theorem. Well, tree width, the grid theorem, and finally the flat wall theorem, and well, many more later. But in order to go to the flat wall theorem, I'm going to discuss the equivalent notions in graphs with perfect matching. So definition of perfect matching, the composition, actually, let's completely skip this slide. Let's go directly to the hand-drawn figure. So a perfect matching decomposition is basically a pair, which is a cubic tree, and a function, which is an isomorphism between the leaves of the tree and the vertices of the graph. Maybe it's better to write it as B of G. So, for example, in the branch decomposition on the leaves, I think we would have edges. Now we put vertices. And of course, its edge of the tree corresponds to a cut. And actually, we consider all the edges that have one side on one side of the tree, their other side is on the other side of the tree. And the width that we assign to this edge is basically the following. We consider all the edges that go over, and for every matching, we see how many of these edges belong to the matching, for all of them. And the measure that we put here is the maximum over all perfect matchings. So that's the weight of that we assign to every edge. And what we want to do is we find a way to minimize over all the compositions the maximum weight. So perfect matching width is actually the analog of tree width for us. And if you consider actually graphs with perfect matching and their directions, their m directions, directed tree width and perfect matching width are bounded with each other. One bounds the other. So grid theorems. Well, there is a function for every bipartite graph. If the perfect matching width is big enough, then we can get the t times t grid as a matching minor. I'm not going to go draw the t times t grid. And similarly, for the directed case, if the directed tree width is big enough, then the directed grid will be contained as a butterfly minor, and this is the directed grid. Basically, we've got t concentric circles all going in the same direction, and we've got 2t paths crossing them, which are, however, alternating in direction. They're going down, up, etc. And those two theorems actually give us already that if a perfect matching width of a graph is big enough, whenever the graph of course is bipartite, we can find in it a wall. Not a flat wall, just a wall. It would be very nice if we could say, okay, we directly got our flat wall, but it's not the case. So we get a large wall, and this is what the long wall, looks like for us. Basically, the reason that I showed the directed grid before is that, in a sense, if we contract the matching edges, we actually do get this direction. We get directed cycles that go, let's say, from white to black, and this would create a path going up. This would create a path going down. and our flat wall, so if our perfect matching width is big enough, we already have a wall in the graph. And our theorem says the following. If we have a large wall in the graph, if we're given a large wall, then two things can happen. Either we can use the vertices of this wall and some jumps in the wall to create a KTT matching minor, which the model intersects W quite strongly, or we can find a set of vertices. I have a picture later, I'm just giving a warm up. Now we can find a set of actually vertices and edges such that we can find a subwall which is flat. So basically what happens is that we kind of use some things from the directed flat wall theorem to prove our flat wall theorem. But what happens there is that we're finding a wall, and then we have to travel in different components in order to find our flat wall and get all the nice properties that we want. Here, whenever we find a wall, we can use this wall and inside find actually a flat wall. So let's discuss what this means. We find the wall, okay. So the first thing that we think there is what happens if we have many jumps in the wall. If we have many jumps, we are able to construct the KTT minor. That's pretty much the idea. However, if we don't have too many of them, we can actually find a set of vertices, which are the apices and are M conformal, such that after we remove them, the wall that remains is flat. Now, what does flat mean? First, we have the perimeter, right? The perimeter bounds the wall. It kind of tells us where the wall is, what is outside of it, what is inside of it. But we have removed some edges in order to find it. And whenever we remove edges, we actually have no guarantee that the rest of the graph has a perfect matching. Actually, there might be the case that because we have something outside, we have some edges in here which do not belong to the matching. We can forget them, we can discard them. Also, what we do next is we apply tight cut contractions. We find tight cuts and we contract. And we keep contracting and we find braces. Now what happens is that whenever we cut among tight cuts, the wall will kind of be pushed towards one specific brace. And what we want is that the brace that actually contains the wall is Pfaffian. It does not contain K33 as a minor, as a matching minor. There is a reason for that. Actually, while graphs with perfect matchings and digraphs are similar, when we go to the notion of flatness, when we're discussing their flatness, they behave more than regular graphs, than simple graphs rather than directed graphs. So the similarity kind of ends here. For example, while we can eliminate all jumps in undirected graphs, in directed graphs, we can have some very few rows where we allow some small jumps. Like we have some short jumps within some few rows of the wall. And these jumps are actually not enough, or at least we couldn't find a reason why they were enough. We could not find a way to use them in order to construct a KTT minor. So in the directed case, our notion of flatness is a bit more loose in the sense that we allow some jumps. In the undirected case, however, we cannot do this. There is a theorem that actually says, the notion of flatness says that whenever you give me the wall and you give me the perimeter of the wall, if I consider the corners of it, let's call them S1, S2, T1, T2, the notion of flatness kind of asks and also asserts, we know that if the wall is flat, there's not going to be two disjoint paths joining the corners of the wall. Now, in graphs with perfect matchings, we can actually claim, we can ask for something similar, and this is where K33 comes. actually, whenever we have a cross, this cross will be inside the K33 model. So let me use the last slides to actually explain why we use K33, why we need K33. Oh, yeah, sorry, I forgot one more slide apparently, which is that we can use the characterization to show that whenever, since this is Pfaffian and does not contain K33, it means that we can kind of glue all the braces together with 4 cycle sums. So let's discuss about paths. Whenever we have a cycle, a conformal cycle, this cycle has a matching cross. Like whenever we can find the 4 vertices, we've got the cycle, we've got the vertices S1, S2, T1 and T2. And we've got 2 disjoint paths that are alternating with the matching, which means that we go between edges outside and inside the matching. They are disjoint and they create a cross over the cycle. So now, actually, we cannot find a very nice characterization. I would think about crosses in directed graphs, since it's kind of related to finding a nice algorithm for the 2 disjoint paths problem, which is NP-hard on directed graphs. However, in the case of graphs with perfect matchings, we can actually describe, like we can prove, and we have proved such a theorem. Okay, and here is a nicer example. We've got the cycle over here, and we've got the 2 disjoint paths connecting the cycle. And this cycle, of course, does not bound the face. So I will not discuss about the general case, but in our case, if we're given a brace, which is basically, again, a bipartite graph with no tight cuts, one of the tight cuts are trivial, and C is a cycle in G, then actually C is a subgraph of a minimal K33 matching minor model whenever G contains K33 as a matching minor. So if we contain K33 as a matching minor, we can actually put the cycle inside such a model and use the vertices and the paths of K33 in order to construct our cross. So in order to ensure that we have no crosses in the flat sense, in the sense that we want it for, we have it for general graphs, for simple graphs, we actually have to forbid K33 matching minors. So basically what happens is that when we cut along tight cuts, we can still have some crosses, but these crosses do not interfere with our flat wall. We will never be able to construct those crosses. And these are results from a different field. So this is all I wanted to say. And I hope I was not too fast. I usually talk too fast when I'm nervous, and I'm always nervous when I'm giving a talk, so I have to apologize. Thank you very much. And here's a picture of snowy Athens, actually suburbs of Athens.
Wow, yeah, that's such a good picture. Thank you so much, Archontia. Let's do a round of applause if everyone can please unmute, and then I'll count to 3 and then we'll clap. 1, 2, 3. Excellent, thanks. And does anyone have any questions?
Are there any problems to do more about this study of open problem questions, or is it possible to apply in hypergraph or getting some relation between these parameters?
I've not worked in hypergraphs at all, so I'm not sure how to translate them. I think that I think that my co-author with another student from Berlin and some other people have discussed hypergraphs a bit, but I'm not sure. I've considered like the relation with directed graphs, but I don't know about fiber graphs. There are definitely many open problems in terms of algorithms and the structure of other structural theorems.
Thanks.
I was going to ask, so in terms of pushing further on to get a full structure theorem, like the graph minus theorem, do you know of any sort of structures that are different, or are you expecting something very similar to the graph minus structure theorem?
Actually, that's a project we've been thinking about, discussing about, but we haven't really started it yet. Like, so at the moment, I cannot give you a general idea of how I would expect a general theorem, like a general structural theorem to look like. There are some approximate results that we can get from our theorem.
So one question I've wondered about is if you're inside one of these matching minor closed classes, whether you would be able to count the number of perfect matchings. So it'd be.
I'm sorry, can you repeat this again?
I was wondering if you'd be able to count the number of perfect matchings if you're in a matching minor closed class.
Okay. So for planar graphs, for example, it's known, it's in P. That's from the characterization of Pfaffian bipartite graphs.
Yes, that's why I came up with the question. So
there are some
I'm wondering
results.
if you exclude an arbitrary thing.
So actually, there are some recent results that say that whenever you exclude, of course, planar graphs, and whenever you exclude any graph that has a single crossing, you can show that it's in P. But in like general minors, the usual minors as we think about them, for K8, it's actually NP hard, I think. It's hard. It's not expected to be polynomial. But for matching minors, I think it's an open question for most cases. Deciding the Pfaffian orientations.
Yeah. Yeah, I was wondering whether vortices would be an issue.
If it's okay, I can give maybe some.
Yes, please, because yes, this is Sebastian Widereft, I think, who talks. He's the one who actually linked me the results that I mentioned right now.
Yeah, sorry, I won't turn on my camera because I'm currently down with COVID, so you will just see my sickly face. So in terms of your structural question, Jim, I don't think that we are going to find anything more than essentially apex vertices, vortices, and bounded genes. I think it's more or less the same thing.
Nice.
Just replace like the small click sums by 4 cycle sums, and then you should get something similar. And regarding the complexity question, so the complexity result Archontia mentioned for general minors does not translate into the matching setting, but it might be possible to adapt the proof technique. So there might be some line where it goes from being tractable to being untractable somewhere in the realm of matching minor closed classes.
So in terms of minor closed classes, do we know when it becomes intractable in terms of vortices and and apex vertices? So if I just remove it, if I have so do vortices by themselves cause problems, or is it apex vertices?
Now you handed it to me. There is actually, we kind of do know. I'm going to present the result on this on Thursday in the seminar of my current group.
I have sent the link is in the chat.
So if you ask, you get an answer. Sorry.
That's great.
It's a very recent result, actually. So it was shown, as Archontia mentioned, like for K8 minor 3 and something beyond, there's a problem, and it turns out the problem is actually the appearance of vortices.
Oh, interesting. So that means it's quite likely to be a problem also in matching minors, but just it might take a bit longer to find, to construct it.
Yes.
Because vortices will still play a significant role the bipartite matching minors, right?
I would expect so, yes. I mean, essentially the vortices pop up as kind of the point where the inductive proof stops. So you can't really go around them.
Yeah.
So I would guess this is right.
Interesting.
Right. Are there any other questions, or maybe I'll end the recording there and then we can have some more informal discussion. Thanks again, Archontia.